Hi, and let's open Module 9, Renewable Energy Forecasting First Steps, with its first block, Generalities and Benchmark Approaches. There, we'll consider wind energy as a basis for the lecture and also for the following blocks. But the same concept, the same ideas could be used also for other type of renewable energy generation, like wave energy and also solar energy. The reason for that is that some of the basic ideas are the same. We'll be collecting quite a lot of data that are observations from the weather or in terms of power, and we also have some input forecasts that are weather forecasts or maybe forecasts for some of the ocean variables like wave height, frequency, etc. Also, we'll use a test case, which is the Klim wind farm. This wind farm is located in the north of Jutland. It is an onshore wind farm that is quite old. It was commissioned in 1996 with 21 megawatts and 35 turbines. The data we had available was from 1999 to 2003, and then the temporal resolution was of 5 minutes originally, which we transformed to hourly averages to fit the market-related application. On top of this data, we also have weather forecasts for wind speed and direction, as well as temperature. The wind farm was actually recommissioned a few years ago, so the setup has changed, and these data do not relate to some turbines that exist still today. Remember that power generation is here normalized, so in practice, power values are between 0 and 1. In terms of general consideration, I will not insist enough on the fact that forecasting is about the future. It may sound straightforward and silly, but still in practice, when we make studies on our laptops with a lot of data available, we may forget about what data is actually available at a certain time and what data is not. So in practice, if we consider we are at time t and we want to predict for lead time t plus k in the future, and there might be quite a few of these lead times, we have to only use the data that's available up to time t. This data may include observations up to time t, power generation, meteorological measurements, maybe some remote sensing information, and then we may have actually weather forecasts that give us a hint about development of the weather situation, but still these weather forecasts are only available at time t. In practice then, since forecasts always have a part of error, we'll just accept it, and the point of generating forecasts based on models and some other ideas is that you try to minimize this forecast error. We do not need to start with very difficult ideas. There's a lot of ways to predict wind power generation and other type of renewable power generation. These ideas might be quite easy, and still the performance might be satisfying. Or at least you have to beat this reference or benchmark approach when you propose more advanced idea. So what do you think is the easiest way to predict wind power generation? What do you think? There may be data-free approaches. First of all, you may want to make random guesses, and it may actually work. We'll see that afterwards. You may also make educated guesses, and that may work fine in certain places of the world and in certain seasons. So think of summer in Crete or all year round in Egypt. You have these thermal effects that make that the wind is increasing from the morning, from when the sun rises, it increases steadily. In the afternoon, the wind stays at a sustained level for quite a number of hours, let's say till 6 in the afternoon, and then the wind is going to lower at the end of the afternoon until the night comes. When you have this kind of thermal effect, the patterns for wind speeds and then wind power generation consequently will be quite similar from one day to the next. So you may actually learn a lot from what you see there and easily make educated guesses about wind power generation. You may also use database approaches. Even though you can collect quite a lot of data, there are very easy ways to use this data to issue forecasts based on the idea of persistence and climatology, which are the two benchmark approaches we'll consider later, but also simple statistical models. So let's start with the random guess approach. At time t, we want to issue forecast for lead time t plus k with k 1 to 48, and for that we'll make random guesses. That means in practice that our forecast y hat t plus k given t will be equal to uk for all k, the lead times in the future. uk is a random draw from a uniform distribution between 0 and 1. So that means we randomly pick numbers between 0 and 1 as our forecast for each and every lead time in the future. Let's look at an example of a random guess forecast for Klim issued on the 28th of April 2002 at midnight. This example is here, so it's a given forecast at time t for lead times between 1 and 48, and power here on the y-axis is normalized power, so between 0 and 1. You may see 1 as the nominal capacity of the wind farm. The forecasts here are in red, and as you expected, they're all over the place. The observations we got a posteriori are here in black with these red circles and lines in between. Visually inspecting this forecast and observation, there doesn't seem to be a good match between the two. It's really all over the place. But what we need to do if we want to actually derive some insight from application of this kind of strategy, we should apply it for a whole sample year, so here 2002, and then analyze its performance. To analyze the performance of the random guess approach, we will assess the quality of this forecast based on the bias, MAE, and RMSE that we introduced in a previous module. Note here that they are all normalized scores, so that means that they're going to be expressed in percentage of nominal capacity. The scores are calculated as a function of the lead time between 1 and 48, and as I was just saying, they're expressed in percentage of nominal capacity. Let's look first at the bias. The bias is this flat dotted line here. There is a bias that is significant. Here it's at minus 25% approximately. If you think of it, it's quite obvious. The bias is for a systematic error you make with your forecast. Here we are issuing forecasts based on a uniform distribution. On average, our forecast is 0.5 since we randomly draw between 0 and 1. For power generation, on average, the power that is produced is the capacity factor of the wind farm. The capacity factor of this wind farm that year was around 25%. So since we are all over the place, the systematic error we make is actually equal to the average power produced over the year minus our average forecast value over the year. So 0.25 minus 0.5. In a scale of 0 to 100%, that's minus 25%. Here also it is flat, since our forecasts are not differentiated for the lead times. We make the same kind of forecast for short lead times and for long lead times. So that means in terms of forecast qualities, this is just the same. We see that effect also for the mean absolute error and the root mean square error. The lines are flat and are actually at very high level. The mean absolute error is at nearly 40% and the root mean square error is at nearly 50%. These are very, very high value. It doesn't look like the random guess approach is a very good one, so I would suggest that whatever forecast strategy you design, you should beat this random guess approach. Then beside that, we can use the persistent approach, or what you see is what you get. When issuing a persistent forecast for all lead times t plus k, k equal 1 to 48, then we use the last piece of information that we have at time t, which is the last measurement, and then we'll use this measurement as a forecast, whatever happens. So y hat t plus k given t equal yt for all lead times between 1 and 48. We see that for the same episode at Klim on the 28th of April 2002, lead times are between 1 and 48, and if we have added this 1 point, lead time 0, which is current time t, and this is the observation we have at time t. I use this observation and I say this is my forecast, whatever happens in the future. It doesn't look that amazing also, like for the naive random guess we had, but still, to derive some information about the performance of that strategy, we should apply it for a whole sample year and then analyze its performance. We use the same scores, and we also plot them as a function of the lead time. Here, the dotted black line is the bias, the blue line is the mean absolute error, and the red line is the root mean square error. Let's start with the bias. Here, the bias is 0 for all lead times. Remember that the bias is for a systematic error. If I use the last measurement as a forecast for any lead times in the future, well, I should not expect that the power is systematically going to increase or systematically going to decrease for each and every lead time in the future. Actually, it's a bit like a random walk. Sometimes it's going to increase, sometimes it's going to decrease, and it's going to vary up and down all the time. So by using the last measurement as a forecast for all these lead times, we don't really make a systematic error. This error seems to cancel out in average. So the bias is 0 for all lead times. In terms of mean absolute error and RMSE, the RMSE is larger than the mean absolute error, which is something that we expected. And here, this scores seems to increase steadily for short lead times, and then at a certain level, they tend to stabilize at a fairly high level of error. The reason why it seems to go down like that here, so the error level is quite low for very short lead times, is that actually this curve starts at 0 if you consider a lead time of 0. Since you have the latest measurements and use it as a forecast, imagine that if you make a forecast for lead time 0, your forecast error is 0, literally. So you would start from 0 here, and then it degrades steadily with the lead time. Now we can generalize that idea, and instead of taking the last measurement only, we could consider an average of the last m measurements. So it's called the m.point averaging forecast, and we're going to apply this strategy here. In practice, this translates to saying that the forecast y hat t plus k given t is the average of the last m power observation, and then we use this average for all lead times in the future. Same episode that we plot here on the right, we're going to show for this episode the average of the last 3 measurements. Before, this was our last measurement at yt, and the persistence forecast was just going flat from there. Now, these are our last 3 measurements. I take the average of these 3, and this is now my forecast for all lead times in the future. It is a flat curve again. It doesn't look amazing, but let's see how it does by applying it over a whole year of 2002 and analyze its performance. Well, when we focus on RMSE only, since it is not that interesting to look at all score, we see that depending on the number of points we average over, this has an impact on forecast accuracy overall. So we have 3 examples here. M equal 1, we only take the last measurement, so that's persistence. M equals 3, that's the example we showed before, so that's the average of the last 3 measurements. And then M equal to 20, so that's the average of the 20 last measurements. We look at the impact on the RMSE as a function of lead time. So lead time values are here between 1 and 48. As we increase the number of points we average over, we see that the performance degrades for short lead time. So this curve at the bottom is for persistence. Here it's for M equal 3, and here it's for M equal 20. The fact that it degrades is that we miss somehow this inertia in the wind power dynamics that we have by doing persistence, and by averaging we tend to account for more statistical averaging of the power production. However, when we go to further lead time, what we see is that persistence is the worst, and then as we start averaging over more and more points, the performance improves. So by doing this kind of averaging, we degrade the forecast quality over short lead time, but we improve forecast quality over longer lead times. What would be the limiting case? obviously it would be considering all the past measurements that we had, so having m tending towards infinity. If you consider all your past measurements and take the average of all those, this is what we call the climatology. And climatology is really the standard way to make a base forecast in meteorology. For all the lead times, k equal 1 to 48, you use the average of all the information ever available. And actually, if you think of it for a wind farm, this is the wind farm capacity factor. So you calculate your wind farm capacity factor and you say that's your forecast, whatever happens. This translates to y hat t plus k given t is equal to the sum of all the past measurements that we have for all k. It is going to be a flat line, like this one, except that now it doesn't link to the last observation, the average of a few other observations. It's just a flat line that is always at the same level, which is the capacity factor of the wind farm. We're going to apply this strategy also for the whole sample year of 2002 and analyze its performance. These are the curves we obtained for the scores that we used before: bias, mean absolute error, and RMSE. Something that we observe is that the profiles are flat, like we saw, for instance, for the random guesses, and the values, though, seem to be at a better level. Remember, for random guesses, we were in the order of 40 to 50% of error. Here, it's more in the order of 20 to 25% for mean absolute error and RMSE. And again, the bias is flat, and it should be equal to 0. Here, it might be due to sampling issue, since I calculate the climatology based on the past data from, let's say, 2001, and then I use it for 2002. So if there's a small difference in capacity factor between these 2 years, it will reflect here in the bias. But the bias you would expect should be very close to 0. Here also, the curves are flat because these forecasts are unconditional. And so if you think of the fact you don't try to make different forecasts for different lead times, we will obtain these flat profiles eventually. Now, a few conclusions at this stage. First of all, you can design forecasting strategy, and they don't have to look very smart. These forecasting strategies we discussed are actually difficult to beat. Especially, persistence is difficult to outperform for short lead times, and climatology is difficult to outperform for further lead times. So eventually, we should be able to do something better based on more dynamic approaches and by extracting more information within available data. Now, I would like to invite you to use the self-assessment quiz to check your understanding.